We stopped our last video after vector subtraction, and in this video we're going to start with what we call scalar multiplication. Now we're actually going to find, while studying vectors, that we're going to have three different types of multiplication that we can do with vectors. One, scalar multiplication. We'll then learn about dot product, and eventually we'll learn about cross product. And so this is one of the clear examples where the operation in using the mathematical objects of vectors is different than the operation with real numbers. So for scalar multiplication, we also can call it the scalar product. The idea is that we're going to, in fact, change the magnitude or the length of the vector, and we're going to change it based on magnitude or a ratio of k. So we'll have it be k times the length. Now, if k is negative or less than 0, then we're in fact going to also be changing it to be the opposite direction. So we want to start by, let's give ourselves an arbitrary vector v. So I'll call that v. And then it asks us, well, can we demonstrate the different scalar multiplications of 1/2 v, negative 1v, 2v, and negative 3v? So I'll do my best. These might all be approximate, so I would put about 1/2 v to be right there. If I needed negative v, negative 1 times v, or negative v, would look about there. Now 2v, again, you know, the picture might not be a perfect representation, but I hope that it's illustrating the point. And here's negative 3v. So what's important here is the direction is either the same or opposite. But the magnitude or the length changes. Now I just want to take a moment. Some people might be wondering, well, why does she keep saying magnitude / length? Why doesn't she just use length the entire time? And so we're going to talk about, again in more detail, the idea that we can investigate these vectors in more than just 2 or 3 dimensions. And the thing is that once we get up to, say, R4, or in 4 dimensions, or 5 dimensions, or 6 dimensions, the idea of length as we understand it in our physical world does not actually exist anymore. And so we need to give it a different name, and that's why it's called magnitude. So while magnitude and length are synonymous with each other when we're in 2 or 3 dimensions, it's not when we're in Rn or n dimensions. And as we go on in this unit, we'll find that we really are looking at things in n dimensions. But after that little digression, let's just take a moment to discuss a few things that we can find out about vectors with their scalar multiple. So one thing is that if one vector is a scalar multiple of another, then we would call them collinear. But this also means that as long as our scalar multiple is not 0, they're parallel. Now, this double bar line, I hope you've seen this before, and I'll be using it myself. That's the same as saying parallel. We could say if our scalar is positive or greater than 0, then they're parallel in the same direction. And if our scalar is negative, less than 0, they're parallel in the opposite direction. Now, for 2 vectors, the notion of collinear and parallel are equivalent. And so I might use those words interchangeably. However, once we get looking at maybe 3 vectors together and asking if they're collinear, that's where we'll use the term collinear. instead of parallel. Now, all vectors are collinear to the zero vector because remember, we can assign the zero vector the length that we want it to be based on convenience, but if we start with the zero vector, the only vector that's collinear to it is itself. So now we're going to move on to second section here, and we're going to talk about vectors in our rectangular coordinate system. So up until now, we've been talking about our vectors from a very geometric perspective, but one of the most beautiful things about linear algebra, and especially vectors, is that they are really the link between geometry and algebra. So when we start talking about vectors in Euclidean n-dimensional space, the idea is that we can actually start giving these vectors real number components, and we call these ordered n-tuples, and they're made up of components that are real numbers. But here I just want to emphasize the word ordered. The order of these real numbers inside the brackets is going to be essential. Change the order, you've got a different vector. So all ordered n-tuples are denoted by Rn, just like we saw at the beginning of the unit, and they're called Euclidean n-dimensional space. Now, geometrically, we can think of n-tuples as describing unique points in space, or lines in space, or planes in space. And we can look at these on rectangular coordinate systems, but we really look at these on rectangular coordinate systems in 2 and 3 dimensions, because if you can figure out a very awesome way to show these in higher dimensional space, then you're going to win a Nobel Prize in physics. When we have 2 or 3 components then in our n-tuple, then we call ourselves ordered pairs or ordered triples. Again, do you see that word ordered? That is so important for us to remember that order matters. Now here's the thing. If I wanted to, I could look at things in R1 as one component and tuple, but this is just our set of real numbers. And so I'll tell you a secret, mathematicians are lazy. And so instead of actually writing it as r to the power of 1, we just write it as r. So here's the key idea. Geometric vectors can be algebraically associated with unique n-tuples by giving us the components. And it's this key idea right here that is the link between geometry and algebra. And this is what makes this mathematics so beautiful. So just some examples of some vectors. So now I would give you some components, and I could say you components could be 2, it could be a negative number like -3, but because these are all real numbers and pi is a real number, it could be pi. And these is in R3. So you notice I use the kind of little e as it's an element from the rails in 3 dimensions. Now, if I looked at this vector v, I could have components that are 0. I can have components that are the same, so I have 2 zeros. I can have components that are fractions, and just like above, I showed I could have components that were negative. And this one's in R4. And we also showed that we could have vectors with only one component and it's in the real numbers, but like this is redundant, and we're not going to really study these because we already know what real numbers do, and that it becomes a little redundant for us to write them as vectors.